Are we live? Are we live? I think we're live. Audio's working. No testing today. We got important stuff to do. So we're switching today. We were gonna have a paper stream about a paper that pointed out a specific flaw in the noise schedule of diffusion models, but maybe we don't even need to be paying attention to diffusion models at all because I woke up and, of course, I scrolled Twitter because I'm a degenerate like that, and I found this paper, Drag Your GAN, Interactive Point-Based Manipulation on the Generative Image Manifold. This is a GAN-based paper. Ooh, wait up a second. Did the stream just die? No, it did not. Okay. This is a GAN-based paper coming literally out today. I think today is the 18th, so it's literally that fresh. And these are pretty impressive institutions here. We got Max Planck Institute at Germany, which is pretty legit. We got MIT CSAIL, which is very legit. We got Google AR VR, also very legit. So these are some heavy hitting institutions. This is impressive work, and the demo for this is absolutely insane. Let me pull that up for you guys. There we go. So this is the demo that made me do this, and you can see they're putting a specific point on the image, and then they're editing it. So like, and it's not just moving points around because the GAN is like trying to semantically make sure the image makes sense. So you can see that, for example, I think this example here, the first one is the best one, right? Where when you move the nose, it moves the whole head. It doesn't just move the nose, it moves the whole head. And then when you try to separate the mouth, it actually opens the mouth and generates the inside of the mouth. So, yeah, very, very good and very crazy. So, that's what we're going to be figuring out today. Is we're going to be figuring out exactly how they did this and whether this demo is cherry picked or not, and whether or not we should expect to see this in Photoshop within 6 months. So let's see. Our approach, DragGAN, potentially kind of a weird name because drag here in American English is whenever people dress up like women and then sing on stage. So it's kind of a weird choice of word there. Allows the user to drag the content of any generated image. Users need only to click a few points and target points, and our approach will move the handle points to precisely read their corresponding target points. Okay, so basically you click on two different things. You click on the start and then the end. So it's not a trajectory. It's basically just 2 points, which means it's always going to be a straight vector. Keeping the rest of the image fixed, this flexible point-based manipulation enables control of many spatial attributes like pose, shape, expression, and layout across diverse object categories. Here's the project page, but I did notice that this isn't even working, so... Oh, it does work. Okay, never mind. I stand back. We got the project page here. We got a bunch of demos. Are these even... These links look dead. This one looks alive. Okay. They have it across a variety of different domains. You guys can feel free to DDoS this guy's email with invitations to your AI startup. Hello, Shingang. I have an AI startup, and I would like you to be the first engineer. Okay. Let's see. So this is the abstract. Interesting that there's no... Okay. Let's see. Synthesizing visual content that meets users' needs often requires flexible and precise controllability of the pose, shape, expression, and layout of generated objects. Existing approaches gain controllability of GANs via manually annotated training data or a prior 3D model. It depends on kind of what you mean by controllability of GAN. I've seen controllability of GANs via latent space kind of shaping. So people, this is a famous GAN paper about latent space. At this point, let me see if I can find the right images. Let me see. Yeah, maybe this one. So for example, This is not exactly the image I'm looking at, but people figured out that whenever GANs are using this shared latent space, right, you can look at that latent space, especially the VQ GAN, and you can kind of do this latent space or embedding space math that you see in a variety of different other papers, such as, for example, taking whatever the vector is for smiling woman, subtracting the vector for neutral woman, adding the vector for neutral man, and then you get smiling man, right? So these results are pretty primitive, though, right? So obviously this is the little tiny thumbnail celeb A data sets, and what we're looking at in this paper here is significantly more impressive. This is not one of your old school GANs from 4 years ago. This is a very modern GAN. Like, just the quality of the output is significantly higher. In this work, we study a powerful yet much less explored way of controlling GANs, that is, to drag any points of the image to precisely reach target points in a user interactive method. To achieve this, we propose DragGAN, which consists of two main components: a feature-based motion supervisor that drives the handle point to move towards the target position, okay, and a new point tracking approach that leverages the discriminative generator features to keep localizing the position of the handle points. Okay, so both of these are relatively new. I don't know exactly what either of those means, which means that they're basically new, and this paper's gonna tell us. Through DragGAN, anyone can deform an image with precise control over where the pixels go, manipulating the pose, shape, expression. These manipulations are performed on the learned generative image manifold of the GAN. Okay, so that right there is letting us know that they're doing this in embedding space. They're not doing this in image space, right? The learned manifold. Manifold is basically just you can think of it like a surface in a space. So manifold in 3D. Everyone, you can visualize a manifold in 3D very easily, right? As a human, you can visualize 3 dimensions pretty easily. So, for example, this is what I think of. In my head, when I think of manifold, I'm thinking of this. I'm thinking of basically a manifold in a 3D space. But manifolds aren't constrained to 3D. You can have a manifold in a 2D space. You can have a manifold in a 4D space. You could have a manifold in a 124 million dimensional space, right? And any kind of neural net, what it's really doing is it's morphing, it's kind of like stretching and pulling and compressing manifolds on higher dimensional spaces until they match a specific distribution that is good for a specific problem. So this is an embedding space. An embedding would be a single point on this space, which also corresponds to a vector, right? A latent is also the same thing. It's just a point somewhere on this manifold. Okay. I digress. They tend to produce realistic outputs, even for challenging scenarios, such as hallucinating occluded content and deforming shapes that consistently follow the object's rigidity. So this is, for example, the example here where they open the mouth and it sees the teeth, right? So in a sense, it's hallucinating the teeth, which were previously occluded behind the mouth. So it didn't actually know what the inside of this lion's mouth looks like, but it has some idea of it because it's seen it in the large data set that it's been trained on. Both qualitative and quantitative comparisons demonstrate the advantage of DragGAN over previous approaches in the task of image manipulation and point tracking. We also showcase the manipulation of real images through GAN inversion. Cool. CSS concepts, computing methodologies to computer vision. I don't know what this means. Sometimes papers have like tags. There's certain journals, so this is a SIGGRAPH paper. So SIGGRAPH is actually a lot of the CGI papers. If you guys know the channel, the YouTube channel, 2 Minute Papers, that guy is very much like kind of like a SIGGRAPH kind of guy. You know, he does a lot of like simulation and light transport simulation, and this is the conference for it. Okay. ACM reference format. Cool. Deep generative models, such as generative adversarial networks, GANs. How many references do you think this paper has at this point? Let's see. Ian Goodfellow. This is the guy. We're going to look him up on Google Citations. Here we go. Let's compare it to The transformers, or attention is all you need. Which one do you think has the most citations? Attention is all you need, Google Scholar. Here you go. So, what's the answer? Let's go. Google Scholar. We got 74,000 citations on attention is all you need. And how many do we got for our generative adversarial networks? Only 59,000 citations. So attention is all you need. Slightly more citations right now, 74,000 to 59,000, but both of those numbers are crazy. Those are big numbers. Have achieved unprecedented success in synthesizing random. Jürgen Schmidt-Huber. Is he currently the king? Does he have more citations than anybody else? Schmidt-Huber. I know because he's constantly complaining that all these papers should. Holy shit, dude! LSTMs has 83,000 citations. That's fucking crazy. Nobody even uses LSTMs anymore. Damn. All right, 83,000 citations. He also has another, like an overview paper that has 18,000 citations. Damn, dude, this is crazy. I didn't realize LSTMs literally have more citations than the transformer paper. Okay. In real-world applications, a critical functionality requirement of such learning-based image synthesis methods is the controllability over the synthesized visual content. Yeah, controllability is what people want. And honestly, like, extending beyond this paper, like, imagine this, but rather than having to click on points, you describe it with speech. Right? Like, that technology, it should be fine, right? You should be able to do that. I should be able to describe the paws of the dog, and then using something like a segment anything, I should be able to know that I want these paws, and then I should be able to say, pull them away. Right? I feel like all the pieces that we need to have like fully speech-based image editing, they're all there. Somebody just needs to kind of tie all of them together. He had a beef with Ian Goodfellow, saying it was his idea. It's always his idea. That's the secret. Okay. Social media might want to adjust the position, shape, expression, and body pose of a human or animal in a casually captured photo. Professional movie pre-visualization may require, okay, blah, blah, here are all the different ways that they could use it. To satisfy these user requirements, an ideal controllable image synthesis approach would possess the following properties. 1. Flexibility. It should be able to control the different spatial attributes, including position, precision. It should be able to control the spatial attributes with high precision and generality. Okay. I mean, these are pretty generic definitions. They don't necessarily have a very specific definition. Most previous approaches gain controllability via prior 3D models or supervised learning that relies on manually annotated data. Failed to generalize to new object categories, right? So all that latent space manipulation for cool demos in the Celebrity A dataset doesn't really work for any other thing other than Celebrity A. Control a limited range of spatial attributes. That's also generally true. But I don't know if that's necessarily because of the techniques that they use. I think that the limited use of previous controllable GANs was more the result of just the GANs being smaller and the datasets that they were trained on being smaller. I don't think it has to do with the fact that the actual model architecture or the specific approach that they use is like fundamentally flawed. So that's something to point out there. Text guidance lacks precision and flexibility in terms of editing spatial attributes. It cannot be used to move an object by a specific number of pixels. Depends on how you describe it. I think that is possible. I just think nobody's really done it. To achieve flexible, precise, and generic controllability of GANs, in this work we explore a powerful yet much less explored interactive point-based manipulation. I feel like there has to be other papers that do this, right? We allow users to click any number of points and target points. This point-based manipulation allows users to control diverse spatial attributes and is agnostic to object categories. This approach with the closest settings to ours is user controllable LT, so some paper from 2022, which also had this kind of dragging based manipulation. We consider the control of more than one point, and we require to handle points to precisely reach the target points. How good was this one? User controllable LT. User controllable LT. Okay, so this is the paper that they're referencing, this 2022 paper that tried to do something similar. This is literally the same fucking paper. Look at that. Look at the difference that viral marketing does. This paper here gets posted on Twitter. We got 2.3 million views within literally 8 hours. This paper here, which seems to be largely the same exact thing. Look at that. You click and drag, the cat goes down. You click and drag the paws. You click the ears. It's basically the same paper, just slightly outdated technology. 20 stars on GitHub. Like, damn, dude, that just sucks. Like, this is the problem with machine learning research right now, is that it's not about the idea, it's not about the concept, it's really just about the one GIF, the one picture, and then whether or not you get lucky and people on machine learning Twitter find it. Because if they don't find it, you're just going to end up like this random dude here, Endo Yuki T, who just made all this work, and then he just got 20 stars on GitHub. No one ever cared again. But largely, this is almost identical. Like, look at this. This is basically the same shit. It's a little bit less good, but you know, it's also 2022 technology versus this paper is 2023 technology. So, compared to it, the problem studies, blah blah. We require handle points precisely. We show that experiments handling more than one point enables much more diverse manipulation. Cool. To achieve such interactive point-based manipulation, we propose DragGAN, which addresses two subproblems: supervising the handle points to move towards the target, and tracking the handle points so that their positions are known at each editing step. Key insight that the feature space of a GAN is sufficiently discriminative to enable both motion supervision and precise point tracking. So it's not just that the feature space of a GAN is sufficiently discriminative. I think something big is that the feature space of a GAN is meaningfully interpolatable. Right, is that if you move around, if you think, let's open up our manifold in 3D, right? If you think about it, you have some latent space that the GAN is doing stuff in, right? And you have a point here that maybe represents the line with its mouth closed, and then you have a point here that represents the line with its mouth opened. The fact that you can move in this space from point A to point B, and that every kind of intermediate point in there kind of looks okay, right? It's like that is a little bit crazy. I think that's the crazier part, is that you can move around in these latent spaces, and every intermediate thing kind of looks okay. Like look at as you move this, it mostly looks okay, right? I don't know. I think that's something crazy that people don't think about. That is achieved via a shifted feature patch loss to optimize the latent code. Latent code, sometimes what they're referring to there is the fact that these latent spaces are quantized into these code books. That's what the VQ VAE did, and taking a latent space and chunking it up into these little codes is very popular. Each optimization steps leads to the handle points shifting closer to the targets. Thus, point tracking is then performed through the nearest neighbor search in the feature space. Okay, they're starting to let us know a little bit more about what they're going to be doing. The optimization process is repeated until the handle points reach the targets. Okay, so you have a multi-step process here. There's an iterative nature to what they're going to be doing. Allows users to optionally draw a region of interest to perform region-specific editing. DragGAN does not rely on any additional networks. It achieves efficient manipulation only taking a few seconds on a single RTX 3090 GPU. Dude, where is the GitHub for this? I need the GitHub for this. Are they going to release this? Code. Oh shit, dude, we're here. We're here. Oh no, there's nothing here. This is a GitHub repo, but it's literally all it has is the GIF and then a README. Fuck. When is this? Let's watch it. Let's hit this little watch button. So as soon as they push a new commit, then we'll hear about it. Yeah, this is just the kind of boilerplate right now. Okay, we conduct an extensive manipulation or evaluation of DragGAN on diverse datasets. Our approach effectively moves the user-defined handle points to the target points, achieving diverse manipulation effects across many object categories. They keep pointing out to the fact that it works with a bunch of different categories, but this paper here, the one that we did, or the one that we were looking at, this is also a bunch of different categories, right? You got cats, cars, houses, faces, drawings, so I don't think this is as impressive as they think it is. Our deformation is performed on learn image manifold of a GAN, which tends to obey the underlying object structures. For example, our approach can hallucinate occluded content like the teeth inside a lion's mouth and can deform following the object's rigidity like the bending of a horse leg. We also develop a GUI for users to interactively perform the manipulation by simply clicking on the image. I wonder what they use for this GUI. I'm kind of getting sick and tired of grad.io, to be honest. I've never been a UI person, so to me, the grad.io is kind of what I've been using for my personal projects, but I really don't like it for many reasons, and I'd love to kind of be introduced to a better UI language and kind of framework, and I feel like this could be cool. This looks like a UI that could be interesting. We'll see what it is once they post the code. Furthermore, our GAN-based point tracking algorithm also performs existing point tracking methods. Our approach also serves as a powerful tool. Okay, related work. Generative models for interactive content creation. Most current methods use generative adversarial networks or diffusion models for controllable image synthesis. Yeah, I would say diffusion models are a little bit more popular now, but generative GANs are making a little bit of a comeback. Unconditional GANs. So conditional is whenever you condition the generation on something, right? So you can condition it on a piece of text. You can condition it on a vector that represents a class or a category. There's a million different ways that you can condition a neural network, and conditioning is basically you're just another way of saying that we're providing an additional input. So unconditional GANs is a generative adversarial network that is not conditioned on anything. GANs are generative models that transform low-dimensional randomly supplied latent vectors into photorealistic images. So what do they mean by here? So much like you in a diffusion model, you start from basically a bunch of Gaussian noise, which looks like basically snow on a CRT TV, and you start from that, and then it just kind of creates the image. It like pulls the image out of the universal kind of entropy. GANs are doing a similar kind of thing, but they're similar in the way that they're basically you're starting from a vector of quote-unquote noise, right? But that vector can also be from a latent space, which is where you start getting the kind of more interesting behavior here. They are trained using adversarial learning and can be used to generate high-resolution photorealistic images. Most GAN models like StyleGAN do not directly enable controllable editing of the generated images. StyleGAN, very popular GAN repo because it's very popular paper because it has a very good repo, so people tend to use it as a benchmark or baseline because they can just use the code in the StyleGAN repo. Which is, hey, if you guys are researchers and you're trying to make sure that people, that you get a lot of citations, right? If you're part of the citation world and the citations are what bring bread to your table and feed your family, make sure your GitHub repo is nice and make it very easy for other people to use your GitHub repo so that they can use it as a baseline and then you get the citation. A little something to do there. Conditional GANs. Several methods have proposed conditional GANs to address this limitation. Here the network receives a conditional input, so it gets an additional thing. And it could be anything. So for example, they have some examples here of segmentation maps, 3D variables. Instead of modeling the conditional distribution, DragGAN enables editing by first modeling a joint distribution of images and segmentation maps and then computing new images corresponding to the edited segmentation maps. Okay, so people have tried weird things with conditional GANs, including some kind of segmentation map. So a segmentation map is an image. I don't know if I need to necessarily explain this, but why not, right? This is what a segmentation map looks like, right? You're basically taking an image and then you're telling me which parts of the image correspond to different semantic concepts such as road, car, person, things like that. Bam. Controllability using unconditional GANs. Several methods have been proposed for editing unconditional GANs by manipulating the input latent vectors. Right, so rather than just feeding it a vector of random noise and then the GAN just generates an image based on that random noise, you can be careful about the vectors that you feed into it and shape the space that those vectors come from, right? So they're no longer just a vector of random noise, they're now a vector from some specific latent or embedding space that you want, right? You want to find a meaningful latent space, a latent space where individual directions have some specific meaning, right? Other approaches compute the important semantic directions in the latent space by an unsupervised manner. The controllability of coarse object position is achieved by introducing intermediate blobs or heat maps. All of these approaches enable editing of either image-aligned semantic attributes or coarse geometric attributes such as object position and pose. So semantic attributes here refers to things that have semantic meaning. Editing in style showcases some special attributes editing capability. It can only achieve this by transferring local semantics between different samples. In contrast to these methods, our approach allows users to perform fine-grained control over the spatial attributes. So I think maybe what they're talking about here is that previous approaches, if the way that you were conditionally generating stuff was by messing with the input vector to the GAN, you can mess with the input vector to the GAN, but you're not going to have fine-grained control over where it ends up, right? So you can say, I want the picture of this face, and I want to move the latent vector that's used to generate this in the direction of making this person younger or something like that, right? So you can manipulate the kind of semantic input, but you don't really have any control over what it's going to do to this image. Versus here, what they're talking about is fine-grained control over the spatial attributes. So in this paper, you can actually go and say, I want this exact part of the nose to move to this exact place over here. So going beyond just semantic manipulation to now fine-grained spatial manipulation. GAN warping also uses point-based editing. However, they only enable out-of-distribution image editing. A few warped images can be used to update the generative model such that all generated images demonstrate similar warps. No yerba mate today. I'm going straight espresso. And little quick digression here. If you're drinking coffee, it's all about light roast versus dark roast, because dark roast just tastes bad. It tastes burnt. And then you also want whole bean. You don't want pre-ground. And then you also want single origin as much as possible. So those are the three things I look for in coffee. I look for single origin, light roast, whole bean. Okay, and that concludes my digression. Let's get back to it. GAN warping also uses point-based editing. However, they only enable out-of-distribution image editing. Preach. Is that what you drink too? Every dream? Are you a coffee person as well? A few warped images can be used to update the generative model such that all generated images demonstrate similar warps. This method does not ensure that the warps lead to realistic images, and it does not enable controls such as changing the 3D pose of the object. Similar to us, a different 2022 paper enables point-based editing. Oh, this is the one that we were looking at. By transforming latent vectors of a GAN, this approach only supports editing using a single point and does not handle multiple point constraints, and the control is not precise. Okay. 3D aware GANs. Several methods to modify the architecture of the GAN to enable 3D control. Here the model generates 3D representations that can be rendered using a physically based analytic renderer. However, our control is limited to global pose or lighting. So I feel like I vaguely remember some of these papers, but there was papers where basically you could manipulate the latent space to get the lighting on an object to change. I feel like I remember that. Like basically, you could have a picture of a person with lighting going this way, and then you have a picture of a lighting going this way, kind of thing. But they don't really seem to spend a bunch of time on that, so let's keep going. What do they have to say about diffusion models? More recently, diffusion models have enabled image synthesis at a high quality. Look at that. They're putting the original diffusion paper here, the 2015 one. That's kind of cool. These models iteratively denoise on randomly sampled noise to create a photorealistic image. Recent models have shown expressive image synthesis conditioned on text inputs. This is really what launched the whole generative AI revolution here, to be honest, is the fact that text conditioned diffusion models were actually really, really good. Natural language does not enable fine-grained control. I disagree with this. I think you can do it with natural language. I just think people haven't really done it yet. I totally feel like the future of image editing is going to be audio based. I think that you're going to talk to a computer. You're going to be talking to it and saying, "I want this face. Get rid of the smile. Add the nose. Add a third eye. Make him older. Make him this thing. Make that." Right? I feel like we're so close to that. All the pieces are there, and someone just needs to put all those pieces together. And I feel like we should that'll be the future. In addition, current diffusion models are slow since they require multiple denoising steps. Everybody loves to shit on diffusion models for this exact reason, right? You have to basically iteratively remove noise over potentially 1,000 steps, although in practice, I think usually it's like 10 steps, something like that. Versus a GAN, you don't need to do that. The GAN is one step, just boom. You give it that little latent vector, give it that little noise, and it'll just one shot generate the entire image. Point tracking. To track points in videos, an obvious approach is through optical flow estimation between consecutive frames. Dude, optical flow is fucking gross. I'm just gonna go ahead and say that, like, is a classic problem. Like all the like classic computer vision approaches for optical flow are just so gnarly. It's no good. There are deep learning based optical flow techniques, but conventional approaches solve optimization problems with handcrafted criteria. Deep learning-based approaches started to dominate the field. Yeah, I'm not like super well versed on optical flow with deep learning, to be honest. These deep learning-based approaches typically use synthetic data with ground truth optical flow to train deep neural networks. That's kind of cool. Among them, the most widely used now is RAFT, which estimates optical flow via an iterative algorithm. Maybe we need to read this paper. He references it twice. RAFT optical flow. Recurrent all pairs field transforms. Code is available at this URL. Let's see. Let's give this a star. Okay, so you get 2 frames. You're feeding it into a neural net. You're concatenating them, or maybe just combining them. You're feeding them at different levels of a kind of a hierarchical looking neural net, and then you get the optical flow. So this is what optical flow really looks like. So optical flow is basically how much each part of the image moves, so, and what direction it moves in. So it's basically like a little vector that you apply. Every single point is going to have an associated vector with it that tells you which direction the object is moving. I wonder if that's what they're doing here. Which estimates optical flow via an iterative algorithm. Instruct pix-to-pix sort of gives him a third eye. No, maybe not, but that well it tries. Yeah. Everybody's got a third eye, secretly. Combines iterative algorithm with a conventional particle video approach, giving rise to a new point tracking method named PIPS. PIPS considers information across multiple frames and thus handles long-range tracking better than previous approaches. Okay, so in this work, we show that a point-based tracking on GAN-generated images can be performed without using any of the aforementioned approaches or additional neural networks. This is interesting, because I think part of the problem with these types of papers is that a lot of times the demo is really cool, but then you go in and you dig into the paper and it's like this 20-step multi like 10 different networks all feeding different outputs, and then you train them all separately at different times, and then the actual process to do inference involves like 10 different steps that are all separate. So these things can get very complicated very quickly. So right here, the fact that they mentioned that they're not using any additional neural networks, it's got me excited because I want this to be simple. I want this approach to be simple, but we don't know yet. It could be very complicated, which would suck. While some previous works also leverage the discriminative feature in semantic segmentation, we are the first to connect point-based editing problem to the intuition of discriminative GAN features and design a concrete method. Somehow I doubt that. Getting rid of additional tracking models allows our approach to run more efficiently to support interactive editing. Despite the simplicity of our approach, we show that it outperforms state-of-the-art point tracking, including Raft and PIPs. Ooh. Ooh. I like this sentence. Despite the simplicity, we outperform state-of-the-art. That's a banger sentence right there. That's what you want to hear. You want to hear something that says, our approach is so simple, and yet it still achieves state-of-the-art. That's what you want. Method. This work aims to develop an interactive image manipulation method for GANs where the users only need to click on the images to define a pair, a handle point, and a target point. Our study is based on the StyleGAN 2 architecture. Okay, so there you go. Remember how earlier I was saying make sure that if you have that when you make a project, you have a good GitHub repo so that people use your code, and then you end up getting more citations because of that. Look at that. This Caras et al. 2020 paper for the StyleGAN 2, they literally use that architecture. That's what you want. That's what open source machine learning is all about. It's about people using your code in the future for purposes that you didn't even really know. StyleGAN terminology. In the StyleGAN 2 architecture, a 512-dimensional latent code, so this is the vector that is fed into the generator, and it's Z, and Z is defined, here you have a normal distribution centered on 0 with identity variance, right? So it's a normal distribution in 512-dimensional space, right? So here you have a normal distribution, right? Everybody knows this. Everybody knows this, their favorite normal distribution. This is a normal distribution in 1 dimension. A normal distribution in 2D looks like this. This is what a normal distribution in 2 dimensions looks like, right? This is a normal distribution in 512 dimensions. So try to get your monkey brain to visualize that. What does a 3-dimensional normal, or a 512-dimensional normal distribution look like, right? Is mapped to an intermediate latent code W. Okay, so then they're mapping it to a different thing called a latent code W. So they have 2 different latent codes here. The space of W is commonly referred to as W. So this latent code small w exists in a space big W. W is then sent to the generator G. Generator is going to be a neural network to produce the output image I. So the neural network takes this little latent code W, small w, and the generator is a function, right? At the end of the day, a neural network is a function. It takes some input and maps it to some output. It takes an input space, maps it to an output space. So it takes this little tiny latent code W from this W space and maps it to an output image I, which exists in some image space. That third eye could come in handy. Yeah, use your third eye to visualize higher dimensional normal distributions. I've actually tried to do that. I think that's a good exercise. And you have to start small. So start with 2D, and then go from 2D to 3D, and then 3D to 4D. You can basically you can get yourself to imagine it. So just like you close your eyes and you just try to like think about taking some 3D manifold and then getting it to be a 4D manifold. But the jump from 4D to 5D is, I feel like that's where my brain breaks. But apparently, like really hardcore like math people, like hardcore physics and math people can actually do this. Like math professors who've been working for decades, right? Like they can actually visualize things in like 5-dimensional space, 6-dimensional space, 7-dimensional space, which is kind of crazy to think about. And the reason that it's important as a machine learning researcher in computer vision to be able to do that is because I think that all this stuff here, right? This is all 2D, right? This is a 2D image, right? And you can think of nerfs as 3D, right? So what does diffusion in 3D look like? What does a generative network in 3D look like, right? If you can take any of these 2D approaches and then in your head visualize a 3D version of it, you could actually be the person that discovers how to do stable diffusion for 3D, right? The hard part about doing something in 3D is that like the visualization of it just becomes so much more complicated. But if you're able to visualize how these approaches work in 3D and 4D, you might be the one that discovers something like fundamental, like how to do diffusion properly in 3D space. So there's a little bit of motivation to keep your third eye sharp. In this process, W is copied several times and sent to different layers of the generator G to control different levels of attributes. Okay, here the sent to different layers, this makes me think that there's going to be kind of a hierarchical situation where information is not just fed to the input of the generator, but it's fed at multiple layers of the generator. And this is something that you see kind of everywhere. I think the UNet does the best example of this, but a UNet is a type of convolutional neural network, but basically it takes a very wide input, turns it into a very kind of deep input, and then goes back to a very wide input. But you can see how there's not just one path, right? You actually take some of the information here and then feed it directly to this part of the neural net. So this kind of idea of residual connections or skip connections, right, where you skip certain layers and you feed inputs to multiple parts of different models. This is all over the place in deep learning, and you want to do this, right? Because different features are going to have different kind of semantic concepts at different levels within your hierarchy. So feeding this vector W, this latent code, into different layers of the generator to control different levels of attributes, that's a very good and very kind of generic idea, I guess. One can use different W for different layers, in which case the input would be this. Okay, L cross 512. So here they're saying that you have different W's that are being fed at different layers, and those W's are now coming from this larger space, which they call W plus. So W is just the space of a 512 dimensional latent code, but W plus is that same space, but there's L of them, right, where L is going to be the number of layers. So just add an extra L to that 512 dimensional space you were visualizing in your head. This less constrained W plus space is shown to be more expressive. So less constrained, I don't know exactly what they mean by that. Maybe that because it's bigger, there's more space, there's more capacity to contain more semantic concepts in there. I don't know. As a generator G learns a mapping from a low dimensional latent space to a much higher dimensional image space, so your network G, right, your function, your neural net G, which is your generator, what it's doing is it's mapping from this low dimensional latent space to a higher dimensional image space, right? Higher dimensional image space like sounds complicated, but really that just means images. It means pixel space. It means three-dimensional pixels, RGB, and then however many height and width your actual image is. It can be seen as modeling an image manifold. Interactive point-based manipulation. An overview of our image manipulation pipeline is shown in Figure 2. Perfect. For any image I, so you have here is the image I, and you see how the latent code, the space of the latent code is all real numbers. That's what this like fancy script R means. So it's all real numbers and 512 dimensions of that. The image, it's all real numbers, but then 3 by height by width, right? 3 channels where the 3 channels are R, G, and B. That's where this 3 is coming from. And also, the 3 is also arbitrary. The reason that our images are three-dimensional, R, G, and B, is because we humans have 3 cones. We have 3 types of cones in our eyes. We have red cones, blue cones, and green cones. But there's animals that only have 2 types of cones, and then there's animals like famously the shrimp, the mantis shrimp or something like this. The mantis shrimp has 16 cones. It has 16 different types of light cones in its eye. So if we were mantis shrimps in a mantis shrimp universe, and we were reading the mantis shrimp equivalent paper, the image space here would be 16 by H by W. So chew on that. Generated by a GAN with a latent code W, we allows the user to input a number of handle points. Okay, so here's the formal definition of what a handle point is. A handle point is a set of points. Oh shit. A handle point is a set of points pi, where I is the number of points, I guess, and you have y or xpi and ypi. So x and y are the coordinate of those points in height and width space, and you have n of those total points, and then you have basically target points, which is going to be the same exact length. I would have almost defined this separately. I would have said that you have a set of point pairs, and then the point pairs are tied. I don't know why they separated out as two different sets, one set of handle points, one set of target points. The goal is to move the semantic positions of the handle points to reach their corresponding target points. We also allow the user to optionally draw a binary mask M, denoting which region of the image is movable. So the mask in these demos, I think in the demo with the cat or the lion, right? You see how there's kind of almost like a lighter kind of circle here, and I think that's the mask. So they're basically, you have the option of saying, I only want to edit this part of the image, only manipulate this part of the image. And if you notice, the part of the image that's not part of this little like highlight doesn't move at all. Or actually, wait a second, it does. Wait a second. Okay, so you see here, they've only highlighted the face, but look at the butt of the dog here. It changes. That's weird. Because what's the point of a binary mask if the rest of the image is also going to change? That's a little weird. I don't know what's going on there. All right, let me take a quick sip of this coffee, blow my nose, and get back to it. All right. Overview of our pipeline. Given a GAN-generated image, the user only needs to set several handle points, aka red points, to target points, and optionally a mask denoting the movable region. Our approach iteratively performs motion supervision and point tracking. The motion supervision step drives the handle points to move towards the target points, and the point tracking step updates the handle points to track the object in the image. Okay, so you have this kind of alternating process. This process continues until the handle points reach their corresponding target points. So they're going to break this down into a series of discrete steps. I wonder if it's going to be 10 steps or like 100 steps. It's probably 10 steps because this runs on a single GPU in a couple seconds. I'm sorry, I'm like burping into the microphone. It's probably disgusting. All right, so we're starting with this latent code W, right, which is 512 dimensions. We're feeding that into the neural network, which is our generator neural network, which is a function that maps from this latent code space, right, W, into the image space I. So you can see here, you give it the latent code, and it goes boom, and creates this image. Then the user is clicking on these points. So now you have a set of points which contains handles and targets. And that gets fed into whatever this is, motion supervision. So this is either going to be a neural net or multiple neural nets, or maybe it doesn't even have a neural net. We'll see what this is. But that changes this latent code, and it changes it to this W prime. And then that W prime is used to generate an image. And then you have a point tracking. You feed, I guess, this entire image into whatever this point tracking is. And the point tracking updates the points. And then you feed that back into this motion supervision. And then I guess you just generate another W prime. And you have however many W primes. And this kind of two-step approach here gets repeated n times. Okay, that seems simple enough. Given the user inputs, we perform image manipulation in an optimization manner. Each optimization step consists of two sub-steps, including motion supervision and point tracking. In motion supervision, a loss that enforces handle points to move towards target points is used to optimize the latent code. After one optimization step, we get a new latent code, W prime, and a new image, I prime. The update would cause a slight movement of the object in the image. Note that the motion supervision step only moves each handle point towards its target by a small step, but the exact length of the step is unclear, as it is subject to complex optimization dynamics. Yeah, so I wonder what they're kind of seeding this with, right? Like, how much are you going to move the point? How much do you have, like like some kind of cap? Do you have like a maximum, like a clipping? Are you clipping the amount that the point moves? Are you limiting it based on kind of how many steps? I wonder what happens if you click the very bottom corner of this image and then click the very top corner of this image, right? Does that just completely break it? We then update the positions of the handle points PI to track the corresponding points of the object. This tracking process is necessary because if the handle points are not accurately tracked, then in the next motion supervision, wrong points will be supervised. After tracking, we repeat the above optimization step based on new handle points and latent codes. This optimization process continues until the handle points reach the target points, which usually takes 20 to 30 to 200 iterations in our experiments. That's a lot. It also makes me doubt what they're saying here. So they said that their approach takes a few seconds on a single RTX 3090 GPU. So let's say a few seconds is like 2 seconds. 2 seconds is 2 seconds enough to do 30 inference steps on a GAN? I don't know, that seems like a lot. Especially if your image resolution is high. I don't know, something is not necessarily adding up in here. Do they also talk about how much time it takes, like how many seconds per iteration? I think they'll extrapolate. I think if by the time we get to the bottom of this paper, they'll explain the exact amount of times, or the actual duration. But it seems like it's not. It doesn't add up in my head right now. 2 seconds on a 3090 for 30 iterations, where each iteration includes one inference step of a GAN, of a style GAN 2 that's actually significantly large. I don't know. That seems a little sketch. So we'll see exactly what it is. Motion supervision. How to supervise the point motion for a GAN-generated image has not been much explored before. In this work, we propose a motion supervision loss that does not rely on any additional neural networks. Okay, so this motion supervision is not going to be using any kind of neural net, which is good because it means that you can save your GPU memory for the biggest possible GAN, right? Like if you had this same pipeline, but the motion supervision and the point tracking was being done with a neural net, you would probably load that neural net into your GPU memory, right? Your GPU has a limited amount of memory on it, and ideally you want to just fit the biggest possible generator network that you can on that GPU, right? So I think it's actually a pretty good idea not to use any kind of neural network here for the motion supervision or the point tracking, because then you can fit a really, really big generator into your GPU. The key idea is that the intermediate features of the generator are very discriminative, such that the simple loss suffices to supervise motion. Specifically, we consider the feature maps F after the 6th block of the StyleGAN2. Okay, so StyleGAN2 is a neural network. Neural networks have basically a bunch of layers on top of each other. Let me let's pull up a picture of a StyleGAN2 architecture. StyleGAN2 images. All right, I guess this is the StyleGAN2. Maybe it is. I don't exactly know. It says StyleGAN architecture, but I have not read whatever the fuck this blog post is, so this could not be the StyleGAN. But you see we have a latent Z. We have a network that maps it to the latent code W. And then we have here, it seems basically like a StyleGAN is basically a convnet. So you see here convolutional blocks, 3x3 blocks, convnets. and the actual latent code is being fed in at a bunch of different levels, right? So synthesis network, this is probably just the discriminator. I don't know why they called it synthesis. Generally, these are called generator networks, but here they called it the synthesis network. So it's fed in after the 6th block. So they're probably referring to, I don't know, there's maybe 8 blocks of these and then 4 blocks of these, so maybe somewhere here. Maybe it's this one here. That's what they're referring to. Which performs the best amongst all features due to a good trade-off between resolution and discriminativeness. We resize F to have the same resolution as the final image via bilinear interpolation. So bilinear interpolation is actually pretty standard. There's a lot of different types of interpolation whenever you resize an image. So everybody knows the Python image library. Python. Oh my god, dude. I'm all over the place today. Python image library. Interpolation. Interpolation. Alright, I'm not going to find it, but there's a lot of different types of interpolation, and bilinear is actually the cheapest one, I'm pretty sure. So, or I think neighbor might be cheaper, but this doesn't seem like a very fancy type of interpolation. It's not like a cubic or like anything crazy like that. As shown in figure 3, to move a handle point PI to the target point TI, our idea is to supervise a small patch around PI. Okay. So there's going to be a little area around the individual point that they're going to basically constrain everything by. We use this function here, capital omega 1, which is a function of pi and r1, to denote the pixels whose distance pi is less than r1. So they have some random hyperparameter here, some human-defined radius, which they're either going to tune specifically for this application, or they're going to give us some theoretical reason why they pick us this r1. All right, you have the motion supervision loss, which is what this step here is going to be using in the optimization process. What do we have here? We have a L1. So you see here these parallel bars. This represents a L1 loss, which is just simply the absolute value, absolute difference between this and this, right? If this was a 2, it would be an L2 loss, and so on. So you have two different terms here. Your first term is FQI minus FQI plus DI. So what is FQ? FQ denotes the feature values of F at pixel Q. DI is a normalized vector pointing from PI to TI. Okay, so PI is the point, the handle point, and then TI is the target point. I feel like they should have just called it H rather than P. HI and TI, but they called it PI and TI. So TI minus PI over TI minus PI L2 here. This is just a normalized vector, so basically just a vector that points from your red point to your blue point. And F0 is the feature maps corresponding to the initial image. So here Fs are the feature values, which is basically just another way of saying inside our StyleGAN 2, whatever the actual features are. So what's coming directly out of this neural net, right? As you're going up into the StyleGAN, those intermediate features, they're calling them feature maps because they're 2D, because this is a ConvNet, right? So this is the difference between the features at the red point and the difference between the features at the blue point is basically what this is. Yeah. So it's how different does this little area of features here compared to the little area of features here, right? And you're summing it over all QIs inside this omega 1, which is basically all of the points inside this little radius that they've defined. So they define some little radius around that point. So you're summing over all of the little pixels in that radius, and then you're doing this for all points I, because you can have multiple of these points, right? You can have multiple red points, and each red point has to have one blue point. So that's what the two summation points are, is for each of the little radius around each point, and then for all points that you're using. Note that the first term is summed over all handle points, right? That's this right here, over all handle points. As the components are not integers, we obtain fqi plus di via bilinear interpolation. What do they mean by this? They're not integers. I think they're referring to the fact that whenever you have this part here, right, you're trying to find the nearest points. Depending on the size of the image, you might get a different number of points within this radius. So you kind of just use bilinear interpolation to make sure that the points that you're sampling around the original red point is always kind of the same number of points. I think that's maybe what they're doing here. When performing backpropagation using this loss, because di is normalized so it's not integers. So okay, let's what is Q? FQ denotes the feature values of f at pixel q, comma di. What is this comma? It's just we don't really have a good idea of what Q is here, and why is this is a weird notation, Q comma di. Di equals 0 if Ti equals Pi. Okay, wait, no. Okay, so Q is just a pixel. It's a coordinate. So Q is basically two different points. It's basically X and Y. It's a specific pixel. So f of Q is the value of the feature map at that specific pixel. And the problem is that feature maps are not going to be all the same, right? As you go up and down the StyleGAN architecture, the size of the feature map is going to change, right? Which is what they're saying here. We have to resize f to be the same resolution as the final image, right? So here's one way to think about it. ConvNet feature pyramid. So when you move up and down a ConvNet, the size of the features changes, right? So the size of the feature map when you're close to the bottom of the neural net is going to be different than the size of the feature map when you're higher up in the ConvNet. So I think that's what's going on here, is that they're doing this at a variety of different levels within the StyleGAN 2 architecture, but at each of those levels, the size of this feature map changes, so they basically bilinear interpolation to resize all of them to the same size so that they can do the same little approach of denoting all the pixels that have some radius around that specific other point. So this comma here is not this isn't the same thing. This is two separate things. This Q is referring to this part of the sentence, and then this DI is referring to a second part of the sentence. So the DI is just the distance. It's just the vector between the point P and the point T, which is the target point and the handle point. And Q is just a specific pixel within this radius of the actual PI. Okay, I feel like that makes more sense now. This will motivate PI to move to PI plus DI, but not vice versa. Why not just call this TI? In the case of a binary mask M is given, we keep the unmasked region fixed with a reconstruction loss shown as the second term. So binary mask, unmasked region fixed. Right? Something is going on here, right? Because as we saw, that's not the case. We were looking at this paper, or this example, and parts that were outside the binary mask are changing. So something is going on. Right. This is what we were showing, right? look at that. They have this binary mask, which is only covering the face of the dog, but whenever you move forward, it is changing the background. So either this example is wrong, or the binary mask doesn't completely fix the background. At each motion supervision, this loss is used to optimize the latent code W for one step. W can be optimized either in the W space or in the W plus. Masking is applied on the feature map space, so the unmasked region is not perfectly intact. Yeah, I think that's what's going on, is because the masking is not applied in the image space, it's probably applied in the feature space. So at the end of the day, you're still just masking a specific part of the feature map and then sending it to this generator network. So the generator network generates the whole image, right? So that is probably what's going on. W can be optimized either in W space or in the W plus space, whether the user wants a more constrained image manifold or not. The W plus space is basically the W space, but for all the different layers. The W plus space is easier to achieve out of the distribution manipulations. We use W plus in this work for better editability. In practice, we observe that the spatial attributes of the image are mainly affected by the W for the first 6 layers, while the remaining ones affect only appearance. Okay, so this is kind of basic intuition here, but anytime you're dealing with a neural network, like in this case a generator network that is mostly a convnet, the layers at the bottom of the convnet are going to be the ones that are closer to the image, are going to be dealing more with kind of the kind of low-level concepts like texture, positioning, things like that. The higher-level concepts such as dog, cat, ear, like kind of semantic concepts are going to appear at the top, right? So in this work, where they're really mostly, they're not looking to change the high-level concept in this image, right? They don't want this cat to turn into a dog. That's not what they're trying to do. They're trying to do very low-level kind of manipulation. They're basically just trying to say, I want this picture of the cat to basically be the same picture of the cat, but I want this little region here to, rather than have the texture of a nose, I want it to have the texture of the neck, and I want this region here to have the texture of the nose instead of the texture of the neck. So it's like they want the high-level semantic concept to be the same, but they want the low-level kind of spatial texture kind of concept to change. So that's why they're focusing on the lower layers, on the first 6 layers of this generator network. Thus inspired by the style mixing technique, we only update W for the first 6 layers while fixing others to preserve appearance. This selective optimization leads to the desired slight movement of image content. All right, let's look at this qualitative comparison of our approach to user-controllable LT. On the task of moving handle points to target points, our approach achieves more natural and superior results on various datasets. Okay, so I guess this is the input. And then this is the output. So you can see how user controllable LT, you move the dog down, it becomes kind of laying dog. Here it actually sits. This one actually feels pretty good. Like it goes from a move, like the bent legs into the straight legs. This thing here, once you move the hand from being, or the elbow from being in this kind of weird like elbow pose, you see how it actually changes this dress into pants. But with this paper, it keeps the dress. So it doesn't change the fact that it's a dress, it only changes the position of the arm. Which is kind of cool. Because you see how here with this user controllable LT, it's like a lot, not just the image, but like the semantic concept of the image is also changing. Right, so you see here, you're trying to just move the sun, but it's also changing the fact that it's in an ocean. Now it's in a forest. Versus with this paper, you move the sun, and it only moves the sun, but it keeps the entire semantic meaning of the image largely the same. Okay. I guess the user control doesn't use the binary mask. Yeah, I don't really know exactly what this paper does, to be honest, so We could compare to it, but I think they'll probably let us know. Point tracking. The previous motion supervision results in a new latent code W prime, new feature maps F prime, and a new image I prime. Okay, so after you do one step of this motion supervision, you get a new version of all of these. Right? This is what they're talking about here. They do one step of this motion supervision, you get a new W prime, you get a I prime, which is this image, and then you get a F prime, which is the feature maps that are intermediate. So the feature maps would be here, right? The intermediate values of this little generator network here are the F prime, and then this image here is the I prime. As the motion supervision step doesn't readily provide the new precise locations, our goal here is to update each handle point PI such that it tracks the corresponding point on the object. So they generated a new image from this modified latent code, but now they need to make sure that the points are correct, right? Because the points are no longer going to correspond to the original position or the original thing that was underneath that point. Point tracking is typically performed via optical flow estimation models or particle video approaches. Again, these additional models can significantly harm efficiency and may suffer from accumulation error, especially in the presence of alias artifacts in GANs. So, I'm never going to find this image, but GANs have like weird alias alias artifacts. I remember this thing where basically they were like moving the person's face around and you could see that the hair was like static. It was like really weird. I think it might have been this paper. Yeah, this image is really creepy, but I remember this. But they're moving around, and notice how the texture actually stays the same. So you see this? You see how like look at the texture on the stash. It like kind of like moves. It stays consistent relative to the image, and like the actual face is moving, but the texture on the top is the same. And this is the alias gassing or the alias effect in a GAN, right? And this is a paper that did an alias-free GAN, so this is what their version looks like. So you can see how the positioning of the texture with the moves with the face, versus most GANs have this problem. We thus present a new point tracking approach for GANs, the insight that the discriminative features of GANs well capture dense correspondences, and thus tracking can be effectively performed via nearest neighbor search. Yeah, I could see that, but I don't know. There's also potentially issues with that depending on your semantic meaning, right? I could see a situation where the dog is like peeking outside of a door, and then if you move it into the door, then you lose it, right? So the nearest neighbor doesn't. I think it works for some things, but it's not going to necessarily work for everything. Specifically, we denote the feature of the initial handle point as Fi. Okay, so you take that initial point and you get the feature at that initial point, right, where they're using the radius, some radius around that point to clip out a specific part of that feature map. We denote the patch around pi as this omega 2 pi r squared, or r2. So they have two different r's here. They have r1 and then they have r2. Right here they define r1. R1 is for the motion supervision loss. So they have R1 for the motion supervision, then they have R2 for the point tracking. Two different R's there. I would have called these R motion supervision, so RM, and then R point tracking, so RP. That's what I would have called them instead of R1 and R2. I feel like that's a little bit more confusing. But the points around a specific point I is a set. That's what these curly brackets mean. It's the set of all xy, which is coordinates, given that xi minus xpi, so that point, the distance from that point in x to the target, or to the handle point, is less than r2, and the distance in y from the point inside this radius to the handle point is less than R2. So basically this is just a set of pixels all within this radius 2 of the point PI. Then the tracked point is obtained by searching for the nearest neighbor of Fi in that. Okay. So basically what they're going to do this point tracking is they're going to say, okay, we're going to take a point. We're going to get this, all the points, all the pixels in a radius around this. We're going to get the features for all of those individual points. And then we're going to see which feature is the closest to the one that we want. This, it feels like there's, I don't know how that works, you know, because I feel like that could result in a bad thing, right? Like, let's say you're here and you're moving this red point to here, right? And then you look all the way around and you're like, okay, well, the image moved, like, which points are the most similar? It might be the case that you end up moving in the wrong direction. So I think the reason this works is because they're doing it in 30 steps. So every single step is actually so tiny that it works out. But I feel like if you had bigger steps, this kind of nearest neighbor search based in feature space wouldn't work, just because the feature space is really like, what's the difference in feature space between this point here, which is fur, and this point here, which is fur, and this point here, which is fur? Like, all these points are very, very similar. So okay, so the PI is the QI inside this constrained little radius around PI that minimizes the distance, the L1 distance between that point in feature space. Yeah, exactly. And it's also not. So sometimes, for example, you could take a clip model. Like a clip is a we talk about it a lot on this channel, but clip is basically a model that has a really good embedding space because it's an embedding space that has both images and text, right? The distance in clip space is semantic, so there's a meaning there. But here they're talking about the distance in the feature space at an early layer of a GAN, right? So they're not talking about the distance in a clip space where it's been very nicely shaped such that semantic distance means something, right? They're talking about the distance in the feature space of like an intermediate layer in a convolutional network based GAN. So that distance there has a little bit less, you know, I feel like it's a little bit more weird, a little bit more black boxy. It's not entirely sure. Maybe the fact that it's lower in the GAN means that the distance in that feature space is more so the distance in almost like a texture kind of direction, if you want to think of it that way, right? The lower layers are going to be encoding more texture information, so therefore it's looking for the nearest neighbor that has the same exact kind of texture. So maybe that actually helps it. In this way, PI is updated to track the object. For more than one handle point, we apply the same process for each point. Note that here we are also considering the feature map F' after the 6th block in the style GAN. The feature maps have a resolution of 256 by 256 and are bilinearly interpolated to the same size as the image if needed. Which is sufficient to perform accurate tracking in our experiments. I also don't like the idea of resizing a feature map such that like bilinear interpolation in image space is already a little bit kind of sketchy, but bilinear interpolation in feature map space, that's weird. Like I feel like that shouldn't work, and the fact that it works is kind of crazy. Okay, implementation details. We implement our approach based on PyTorch. Goddamn right, PyTorch keeps winning. We use the Atom optimizer, everybody's favorite optimizer, to optimize the latent code with a step size of 2e to the negative 3. FFHQ, AFHQ, and LSunCar. So these are datasets actually here. Let me get rid of this. Let me use the dataset color. FFHQ is a dataset, AFHQ cat is a dataset, and then LSunCar is also a dataset. The hyperparameters are set to be lambda equals 20, so I think lambda was the trade-off that they were here between this term in the supervision loss and this term in the supervision loss. So that's what this lambda is. Or gamma? No, lambda. Yeah, lambda. And R1 and R2. So R1 is 3 and R2 is 12. So this is kind of interesting. So R1 is the motion supervision. So R1 is actually very small. It's just 3 pixels in the motion supervision step. But then when you're doing this nearest neighbor search as the in the point tracking, the R2 becomes much bigger. So this is kind of cool. The difference between R1 and R2 is interesting there. Hello, Kalina, how's it going? Neural networks are essentially feature extractors. On top of them is a linear model, so in some sense the linear interpolation of feature bursts should be viable. Yeah, I could see that. Obviously it works. Obviously they bilinearly interpolated in the feature space of this and it still kind of works, but I feel like maybe part of the reason it works is because these are only the first 6 layers, right? So the first 6 layers are going to be more preserving of the like spatial positioning of that exact image. So maybe that's why it works. I feel like if you bilinearly interpolated in the last 6 layers, it would be much more nonsense. But yeah, maybe the fact that this is just the first 6 layers, so therefore it's kind of closer to image space anyways, it's okay if you interpolate. We stop the optimization process when all the handle points are no more than d pixel away from the corresponding target points, where d is set to 1 for no more than 5 handle points and 2 otherwise. Okay, so they have this other random hyperparameter here called d, which is basically how close the points need to be before they say it's okay. We also develop a GUI. What did you use for this GUI? I need to know. Thanks to the computational efficiency of our approach, users need only wait for a few seconds. Jesus Christ, my nose is super itchy. 1 second. Doing okay, although university is crushing me lately. Yeah, I do not envy you. Looks a bit like Dear Image GUI. I am GUI. C++. Oh shit, this 100%. That's what it is. Oh, you guessed it, dude. Look at that. Damn. That's badass, Oizen. You knew exactly what it was. Alright, we might have to use that. Let's give this a little star. We'll look at it later today. 47k stars. That's actually quite good. You have to write C++ code, though. Dude, you know how long it's been since I fucking wrote C++ code? Believe it or not, there was actually a point in time when I was better at C++ than I was in Python. But that was a very, very long time ago. Now I am way better at Python than I am at C++, and I'm actually afraid of C++ now. Also has Python bindings. That's good. I like that. Not sure if the Python version is good. Maybe not. Probably is trash. Okay, experiments. We evaluate our approach based on StyleGAN 2, pre-trained on the following datasets. FFHQ. So here is the datasets and then also the size of the datasets. I kind of like that. I like this. I like it. I like being able to know exactly the size of the dataset here, or the size of the image in the dataset. And Elson Cat 256. Landscapes HQ 256. Microscope and lion, dog, and elephant. Wow, they have a dog dataset that is big images. Our main baseline is user controllable LT, which has the closest setting with our method. User controllable LT does not support a mask input, but allows users to define a number of fixed points. Thus, for testing cases with the mask input, we sample a regular 16 by 16 grid on the image and use the points outside the mask as affixed points. Okay, we create two variants of our approach where the point tracking is replaced by these two tracking methods. Okay, so what do we got? Real image manipulation. Given a real image, we apply GAN inversion to map it to the latent space of the style GAN, then edit the hair, pose, shape, whatever expression. So there's 4 edits here, and each edit is going to be a 30-step process. So they said anywhere between 30 and 100 steps for each one, right? Because this is an iterative approach. So they move this guy's nose, and then they bring his hair down, and then they bring his cheeks in, his like jawbones in, and then they move his frown into a smile. Which is actually kind of interesting here. If you actually look at it, the original image, he's smiling. And then whenever they shift his nose, he's no longer smiling. That's kind of weird, right? Why does the GAN think that whenever you move your face this way, you're no longer smiling? So it's like, it's kind of creepy. Hairline repairer. I have to get the code for this. I feel you, brother. I am part of the non-existent hairline club as well. Input, pip, raft, manipulation process. This little cat moving. Ooh, this looks bad over here. Raft, look at this. It hallucinated this fucking little patch of lion fur just standing there in the middle of nowhere. And what do we got here? Face landmark manipulation. So face landmarks are basically, landmark is just one of these points. And whenever you're doing like pose tracking, right? This is a very common task. There's also face pose tracking. So a very common model that people use a lot is Google has a thing called MediaPipe, and MediaPipe has this kind of face tracking where you can basically track the landmarks on a face. And there's a bunch of different formats for face points and face landmarks, but I wonder which one they're using here. This actually seems like one of the more simple ones. Our method can manipulate these landmarks to match the landmarks for the target image. That's actually a really cool concept where basically you have two images. You have an input image and you have a target image, and you say, okay, let me take all the landmark points in this image and then all the landmark points in this image and then make all the landmark points in this image the original point and then move them to all the target points. And so now you have a natural way to kind of shift the face into a target face. Yeah, smile direction and view angle are entangled, which is weird to think about, right? Like the distribution, the image distribution of all images on the internet is kind of crazy to think about, how there's certain dimensions are entangled, right? Like there's probably some kind of thing where like if the background is grass, the like leafy background is entangled with someone who is less shaven face, because people with who have nature backgrounds tend to be more hippie, therefore they have a little bit more hair. Like there's probably weird entanglements like that are just like almost impossible to understand as a human. What do we got here? Quantitative evaluation on face key point manipulation. We compute the mean distance between edited points and target points. Okay, so here they're comparing to a couple different pips, raft, and then user controllable LT. Whether you have 1 point or 68 points. Here they're using Frichet inception distance, which I don't like. I really don't like this quantitative metric, but people like it because it's easy to calculate, and then the total amount of time required to do that. So user controllable LT is actually very fast. That's kind of interesting. I guess it's also a GAN, so it also just basically does it in one shot. But this does seem to perform better than pretty much everything. zoom back out. Zoom out again. Qualitative evaluation shows the qualitative comparison between our method and user controllable LT. We show that the image manipulation results for several different object categories and user inputs. Our approach accurately moves the handle points to reach the target points, achieving diverse and natural manipulation effects such as changing the pose of animals, the shape of the car, and the layout of the landscape. In contrast, user controllable LT cannot faithfully move the handle points and often leads to undesired changes. Yeah. This is what we were noticing here, is that it moves it changes some of the stuff in the background. So you see here, it went from ocean to forest, and then here it just randomly started hallucinating this background of trees. And then here, whenever it got rid of this arm, it turned it to pants. So, Kalina, you were talking about entanglement, right? The entanglement here, right, this pose right here, if someone is doing this pose, they're very likely to be wearing a dress. But someone who's doing this pose, probably just wearing pants. Which is weird, because if you think about it, like, this pose is almost like a model pose. Like, I think of like Oscars and like red carpet kind of events whenever I see that. So the model has also made that association where it's like, okay, this pose, this kind of like elbow pose, that comes from people at these red carpet events where they're wearing dresses, which is kind of cool. The entanglement of image space. A comparison between our approach with pips and raft is provided. Our approach accurately tracks the handle point above the nose of a lion, successfully driving it to the target position. Consequently, they move the wrong part. When no tracking is performed, the fixed handle point soon starts to drive another part of the image, and after a few steps, never knows when to stop. Okay, real image editing. We use GAN inversion techniques that embed the real image in the latent space. GAN inversion techniques just means that they're basically taking the image, rather than saying, hey, we have some latent vector, and then from that latent vector, we're going to generate the image, which you just use the generator to do that. They say, okay, well, actually, we want to take an already existing image and then project it into that latent space so that we can then do our little manipulation stuff. So that's what they're referring to here. They're using PTI inversion, and then perform a series of manipulations to edit the pose, hair shape, and blah, blah, blah. We show more real image editing examples in Figure 13. Where's Figure 13? I guess it's down at the bottom. All right, we'll have to wait to get to it. Quantitatively evaluate our method. Can you provide the link for the paper that you're looking at now? It should be on the YouTube video. So in the description of the YouTube video, you should be able to click. It should be there. If not, it's called DragGAN, Interactive Point-Based Manipulation. 2305 1097.3 is the actual archive. What a time to be alive, dude. Yes, dude, heart. Show 'em love, dude. Happy cherry, clap, handshake. I love adding meaningless emojis to conversations. We quantitatively evaluate our method under 2 settings, including face landmark manipulation, paired image reconstruction. Face landmark detection is very reliable using an off-the-shelf tool. Look at that, 2009. I was in college in 2009. That's ancient. We randomly use its prediction as ground truth landmarks. Specifically, we randomly generate 2 face images using StyleGAN trained on FFHQ and detect their landmarks. After manipulation, we detect the landmarks of the final image and compute the mean distance to the target landmarks. I don't know if this is necessarily like a super good benchmark, to be honest. I feel like it's a little bit sketchy, but imagining how this would work within Midjourney, extremely powerful. Yeah. This is going to come soon. Like, I bet you that today, inside the Midjourney HQ, they're going to have a meeting about this exact paper, right? Like somewhere in San Francisco, wherever Midjourney HQ is, Or maybe Midjourney is Midjourney fully remote? Do you guys think it's fully remote? Could it be applied on diffusion-based models? You could there's probably a way to do this with diffusion models. I don't think you're limited to GANs, right? You could take this exact same approach and basically rather than generating from this latent code, you can envision this being a latent feature map, right? Like the latent the way that GANs or the way that diffusion models now work is they basically do the diffusion in latent space, right? So they're also dealing with a little latent. It's not a latent code, but it's kind of the same thing, right? It's like a little latent, like little patch. So you could envision something similar. The problem is it's going to be very slow, right? Because every single time you go from that little latent patch into the image space, you're going to have to do like a 10-step diffusion process. So here, they said that they do this with 30 different steps of this like motion supervision, point tracking, then motion supervision, then point tracking, then motion supervision, then point tracking. And imagine if every single time you did that, you also had to do 10 steps of diffusion. So they could be watching right now. That'd be pretty awesome if Midjourney people watch this YouTube channel, but I doubt that they do. I think they have better things to do. The results are averaged over 1,000 tests. The same set of test samples is used to evaluate all methods. In this way, the final MD scores reflects how well the method can move landmarks. We perform the evaluation with different numbers of landmarks, and we also report the FID score between the edited images and the initial images as an indication of image quality. I disagree. This is nonsense, dude. FID score is not a good measure of image quality, and fuck anybody who thinks that it is. I'm going to die on that hill. Our approach significantly outperforms user-controllable LT. Under different numbers of points, qualitative comparison is shown where our method opens the mouth and adjusts the shape of the jaw. Furthermore, our approach preserves better image quality. Thanks to better tracking capability, we also achieve more accurate manipulation. Okay, so basically it's better than all these other things. Although user-controllable LT is faster, our approach largely pushes the upper bound, achieving much more faithful manipulation. Yeah, it's just... You don't really need benchmarks when the demo is good. If the demo is good and you're doing something that nobody else could do before, who cares about benchmarks? Your demo is the benchmark, you know? Qualitative results are better than quantitative results, right? One thing is getting state of the art on a benchmark by beating the current state of the art by 1% or 2%. That's not that impressive. You know what's really cool is qualitative improvements, right? Is being like, hey, here's what my model did, and I don't even need to tell you what the score is. I don't need to tell you what the FID score is. It's like, as a human, you can just look at this picture and you know it's better than what it exists. The whole paper feels like a diss on user-controllable LT. I think it's more user-controllable LT is just, no one knows about this paper. This is what we were looking at. User-controllable LT has like 20 stars. It's just like some random-ass paper some guy wrote that just got shuffled in and nobody ever paid attention to it again. So if anything, this guy's probably happy. This person here, Endo Yuki T, they're probably psyched that someone finally realized that their paper was doing something. Let's give this person a follow. Where does this person work? Endo Yuki T Animating, SIGGRAPH Asia. So Pacific Graphics. Obviously, this person's somewhere in Asia. I don't know a ton. I'm assuming Yuki and Endo, those sound kind of Japanesey to me, so I want to say this person's somewhere in Japan. But I don't know, kind of a mystery person, to be honest. I'm sure they're happy that their paper is getting referenced here. They have a citation here, so. Specifically, we sample a latent code W1, randomly perturb it to get W2. Let I and I2 be the style GAN images. Okay, wait up. Latent code W1. Perturb it to get W2. You have I1 and I2 are the style GAN images generated from the two latent codes. We then compute the optical flow between I1 and I2 and randomly sample 32 pixels from the flow field as the user input U. Okay, so they're coming up with this kind of like automated way of creating examples, right? So in these examples here, this is like a user that's saying, here's the point that I want, here's the point that I want it to go to. But in order to get like a better quantitative score, they wanted a lot of examples of like, here's a point, move it to point here. So they basically this is the approach that they use to generate 1,000 examples of like what a user could want to do, which is kind of interesting. Our approach, maximum optimization step to 100, so 100 steps for each one, which is quite a lot. Our approach outperforms all baselines. Ablation study, we study the effects of which features to use in motion supervision. We report the performance of face landmarks using different features. So maybe different features here refers to whether they're going higher or lower in the style GAN, right? So you can, the lower you go, the more kind of textury, kind of spatially the features are going to be. The higher you go, the more semantic, kind of high level the features are going to be. The feature maps after the 6th block perform the best, showing the best balance between resolution and discriminativeness. So, okay, we'll see. The provided effects, it can be observed that the performance is not very sensitive to the choice of R1, and R1 equals 3 performs slightly better. Okay, so R1 is the radius around the points in which they're doing the motion mapping. Or, yeah, there's two different R's, right? There's the R for the motion supervision, and then the R for the point tracking. Let's go back down. All right, let's look at these pictures here, or these tables. Quantitative evaluation on paired image reconstruction. We follow the evaluation and report MSE and LPIPs. So MSE is an error, of course, so lower MSE is better, and then LPIPs is a distance, so lower is also better. User controllable LT versus theirs. This method basically beats everything on every data set. So that's also important, right? Sometimes we look at papers and they'll beat other baselines, but only on specific data sets. And that kind of makes me instantly suspicious, because it means, okay, they could have probably picked the data sets such that it looks like their method beats the other ones. But here, when they have 4 different data sets and 2 different metrics, and it beats every single baseline on both of those metrics and all 4 of the different data sets, I think that's kind of irrefutable proof that this technique is better. Effects of the mask. Our approach allows masking the movable region. After masking the head, the rest part would be almost unchanged. Dude, something's going on here. This is weird. You guys noticing this? Look at this. In this picture, they have the dog, and look at the face, but look at, did they edit that out? They fucking edited this out. Look at that. The tail is different too. So here you have the fluffy tail, and then it turns into like kind of a thin tail with this weird little like second tail. But here in this image in the paper here, yeah, look at this. They didn't show you that. It's a little disingenuous, guys. A little disingenuous. You're cherry picking your examples for the demo, you know. But I guess you got to do what you got to do. You know, you got to pay the bills. You gotta hype up your paper. Puffy poop, yeah. I mean, whenever you're like, the problem is that the paper world is fucking brutal, right? Like, this person here basically did this exact same type of thing, but they probably don't. You know what I'm saying? Like, this person, the people in this paper, they're going to get all kinds of offers from Stability AI and Midjourney. They're going to go and they're going to get some big fat 6-figure salary at a generative AI startup. But this person here, who did effectively the same exact shit just a year earlier, might be like some poor grad student with 0 offers, right? So like, the difference between your paper going viral and not going viral in terms of like the financial outcome for you is huge, right? So the paper world is very competitive, and I feel like the viral marketing and like making sure that the picture that you use in your paper is optimal in order to get that pop and that virality is so important. And I feel like a lot of people get screwed over because a lot of people are very good researchers and the ideas are very good, the concept is good, the work is good, the GitHub is good, but it just doesn't catch on, nobody pays attention, and then they're just sitting there laboring in obscurity, and then the one person who made a really cool looking demo, they're the one that gets the fancy research scientist position at Meta, you know? Yeah, probably getting mentioned by AK on Twitter is important, so you gotta pay this guy money, dude. AK. Akali, AKH. I don't exactly know if this is Akali Q or AK Haliq. I don't exactly know what this guy's actual name is, but you gotta pay him money probably. Effects of which feature to use. X plus Y means the concatenation of the two features. Okay, so here they're comparing the different layers, so how far up and down the stable, or how far up and down the StyleGAN 2 ConvNet generator you're going, right? So block number 4 all the way to block number 7. I don't know how many blocks there are total. Maybe there's 10 blocks or 7. I don't exactly know how many blocks there are in total for the StyleGAN 2. But you can see here, it actually doesn't seem to be a huge difference. The 4th block kind of seems like shit, but the difference between the 5th, the 6th, and the 7th block is kind of the same. Table 4, effects of R1. So R1 is kind of the radius of how when you have a point, how many pixels around that point are you using? So again, doesn't seem to make a huge difference. Out of distribution manipulations. So this is interesting. I was actually wondering this as soon as I saw this. I was like, what happens if you click on a point that's all the way in one corner and go all the way to the other corner? Like, is it able to manipulate it? And yeah, I mean, it's pretty good. Look at this. This is a very kind of warped image of the dog, but it actually, or the lion, my bad, but it still seems pretty good. It was able to get a pretty good, it was able to figure out a way to make it work, which is interesting. Discussions. Effects of masks. Our approach allows users to input a binary mask denoting the movable region. We show these effects on figure 8. Without the mask, the manipulation moves the dog's whole body. This also shows that point-based manipulation often has multiple possible solutions, and the GAN will try to find the closest solution in the image manifold learned from the training data. The mask function can help to reduce ambiguity and keep certain regions fixed. Out of distribution manipulation. So far, the point-based manipulations have shown are in distribution. They're very small, and it's possible to satisfy the manipulation requirements with a natural image inside the image distribution of the training dataset. Yeah, like, what happens if you click on this point here, and then move one of them down and one of them up, right? Like, is it going to rotate the head of the dog, or is it going to, like, tilt the head of the dog? Like, what is... I'm kind of like super curious. I need them to release this paper, release this code so that I can play with this, because I'm really curious about how the GAN decides to kind of fix some of these things. It can be seen that our approach is it like a Quasimodo dog, right? Do you guys know this character? This is like a Disney character. Right, he has like an eye that's like kind of like down and an eye that's up. Dude, they have Quasimodo actors at Disney. This is fucking terrifying. Can you imagine being a little kid and then there's like this fucking Quasimodo like coming up and like trying to be like, "Hey, take your picture with me." It's gotta be hilarious, like scary. Would this approach also be one solution for video generation? You could probably do some kind of video generation type situation for this. I think it's video generation is still very complicated, so I don't know. I don't know if you're going to necessarily push the boundaries with video generation using this particular technique, but you could see something. For example, here, you know how they were talking about using optical flow in order to get the points. You could probably do something like that where you can take you can use optical flow between frames in order to manipulate the original frame and then see if that gives you an image that kind of like a video that kind of looks like it moves. But I feel like it's probably still going to be kind of difficult. I don't know. You should try it if you're in the research world and you just finished a paper and you just submitted it and you're thinking about what research you're going to be working on next. That is definitely a cool idea. It can be seen that our approach has some extrapolation capability, creating images outside the training image distribution. In some cases, users may want to always keep the image in the training distribution as it prevents from reaching out of distribution manipulations. A potential way to achieve this is to add regularization to the latent code. Okay, that's actually also a cool idea, adding all kinds of extra regularization losses and terms to the existing losses such that you get better results, sharper results, less weird results. Could get a nice looking golf swing. Yeah, actually that's true. Because the latent space, is there enough images of golf on the internet to get a clean interpolation in the latent space of a GAN for a golf swing? Maybe? Maybe yes, maybe not. I don't know. Despite some extrapolation capability, our editing quality is still affected by the diversity of the training data. Creating a human pose that deviates from the training distribution can lead to artifacts. Handling points in textureless regions sometimes suffer from more drift in tracking, as shown in Figure 14. We thus suggest picking texture-rich handle points if possible. It would be misused to create images of a real person with a fake pose. Conclusion: we have presented DragGAN, an interactive approach for intuitive point-based image editing. Our method leverages a pre-trained GAN to synthesize images that not only precisely follow user input, but also stay on the manifold of realistic images. In contrast to many previous approaches, we present a general framework by not relying on domain-specific modeling or auxiliary networks. Yeah, that you don't need to have a bunch of extra networks that you need to train. This is achieved by using two novel ingredients: an optimization of latent codes that incrementally moves multiple handle points towards their target locations, and a point tracking procedure to faithfully trace the trajectory of the handle points. Both components utilize the discriminative quality of intermediate feature maps of the GAN. So the fact that these intermediate feature maps of the GAN are pretty good, right? That is a good idea, right? It's not entirely intuitively obvious that the intermediate feature maps of a GAN would have enough kind of like information and signal inside of them to be able to do this kind of thing. So the fact that they were able to basically do all of this with the nearest neighbor in feature space of an intermediate feature map of a GAN, you know, that's an idea. That's an idea that a human had that, you know, you got to give them props for that. To yield pixel-precise image deformations and interactive performance, we have demonstrated that our approach outperforms the state-of-the-art in GAN-based manipulation and opens new directions for powerful image editing using generative priors. As for future work, we plan to extend point-based image editing to 3D generative models. Okay, so maybe if you're inside this space and you could be doing an extension of this work for your research, try not to do it for 3D because it sounds like that's what they're going to be doing. So it sounds like the people who worked on this paper, they're going to try to do it for 3D as the next thing. So if you try to do it in 3D, they might beat you to it and they might get a paper that's very similar to your paper, and their paper would obviously get more views than your paper. So maybe try to do, I think doing this with diffusion models is an obvious extension, and yeah, maybe doing this with videos, which is another suggestion that we had. So lots of different ways that you could extend this research. All right, and then here we have more examples. So we have, oh my God, this is adorable. Look at that. They close the little cat's eyes and then they move. It's like, look at this little kitty. It's an adorable little kitty. They turn this dog. They move the elephant trunk. This is even weirder. Doing it on these like kind of like biology slide pictures. And we were talking about entangled latent spaces. What kind of entanglements exist in the latent space of a GAN that's been trained on biological slides. Right? Like, I don't know enough about biology to even know what these different little granules inside this thing are, but I wonder if it understands certain things, such as, like, oh, the shape of this bacteria here corresponds to a specific family of bacteria, so whenever I rotate it, the, like, organs inside that bacteria have this specific kind of distribution. There's so many cool kind of explorations of latent spaces that I feel like you can do with this. Horses, cars, out of distribution poses, more cat pictures. By masking the foreground, we can fix the background. Optimizing the latent code in W plus space is easier to achieve out of distribution manipulations, such as closing only one eye of the cat. In contrast, W space struggles to achieve this as it tends to keep the image within the distribution of the training data. Yeah, so W plus space is the one where it's the space, but the space of the layers, versus W space is just the latent code space. So the latent code space is only for images that are within the distribution of the training data, right? So in the actual distribution of the training data, there is no such picture of a cat that is blinking. So when you're doing it in the original latent code space, it's trying really hard to not give you a picture of a blinking cat, because a blinking cat does not exist in this space. So when you're doing it in the layer space, this W plus space, it doesn't have that same kind of distribution. It's a different distribution, a different space. So therefore you can get a picture of a blinking cat, which is kind of a cool thing. Oh shit, Oizen, that's a very good idea. The audio. Holy shit. Yeah, you could 100% do that. You could 100% do this technique for spectrograms. Damn, Oizen, you better take that idea and run, because someone is going to do that, and they're going to make the next audio generation model. That's a very good idea, Oizen. That's next level. Props to you there. Cool. So that's it, guys. That's the paper. Very awesome paper. Very impressive research groups. Really excited by this paper. I think the idea of the doing this in the feature space of this generator, pre-trained generator, very good idea. I think this iterative kind of approach, not necessarily super intense. Obviously, it's a very simple approach, and they talk about how the fact that it's simple. So I think you're going to see a lot of different variants of this, where people do more tricky things. They replace these things with neural nets. Maybe they use diffusion models. But I feel like the core parts of this paper are very interesting to me. And just the use of this for exploring the latent space of GANs is actually super cool. I think you're going to see a bunch of different companies try to make their own versions of this. A bunch of different research groups try to make their own version of this. And I'm excited, dude. I'm excited to see what comes out of this. I don't have any negative things to say about this paper. The only negative thing I have to say about this paper is that their GitHub repo right now is just a bunch of garbage. All they did was just basically post the README with a GIF on it. You guys need to make this real. Make this a real fucking, put your actual code on here, because I feel like people need to play with this. Like, look at this. Look at this. 28 forks. What are you forking? They're making a fork of a repo that only has a README. What the fuck? Like, people don't, like, I'm pretty sure that there's bots that just go around and fork random repos. Like, why would you make a fork of this when there's literally nothing here? There's no code. All right. we'll leave it at that. Hope that was a fun little paper for you guys. I'm definitely excited. But yeah, we'll see. Drop by the Discord if you want to talk more about this, if you guys have other paper recommendations for next week. If not, you guys have a great weekend. Go out and enjoy. It's starting to get to the summer, so get some sun, get some real world exposure, and yeah, see you guys later. Like and subscribe. Talk